So there's some notes that are kind of reflecting what we did at the end of class on Thursday, starting to talk about the precise definition of a limit. I guess we should get going. It's 10:01. Give me a moment though. I'll get going in a moment. Just need to organize my thoughts here. So if you haven't already, go ahead and scan one of the laminated QR codes, not the paper one there, not the paper one up there, one of the 3 laminated ones that are in front of the chalkboards to fill out the attendance form. Yeah, okay, papers. Cool. Come on in. All right. Oh, I need actual paper. So I was looking at all of your various Co-21A classes, and people are really spread out. Like some people are talking about chapter 3 already. Some people are still, the very beginning of chapter 2, which is, I mean, it's totally fine. We are where we are, but we obviously can't accommodate everyone's stuff. So I'm gonna try to be where I think we should be. If you have questions, I am certainly happy to address them, but we're talking about limits still. And specifically the precise definition of limit, because that stuff can be a bit confusing. Come on in. All right, so let's go ahead and remind ourselves what we talked about last time. And it was not too terrible. Last time we were just saying that if you have a function, in this example, the function is 2x plus 1. If you're trying to find the portion of the function that corresponds to this, that the difference between the function and 7 is less than 1. Also, I should point out, right, just so everyone's on the same page here, the whole idea is we're trying to talk about why the limit x approaches 3 of this function is equal to 7. Right, that's kind of what we start with. Like, yeah, this limit, right? I mean, if you look at it, right, as x is closer and closer to 3, the function definitely gets closer to 7. What we're trying to do is to make that a bit more precise. So what we're saying is, okay, well, how close to 7 do I want to be? In this case, I want to be within 1 of 7. And what we're seeing here is that the function being within 1 of 7 means the same portion of the graph as x being within 1/2 of 3. So I want to point that again, right? If we're looking at this little section right here, maybe I can zoom in so you guys can see this a little bit better. Even more. So we're looking at this section of the graph right here, where the function is between 6 and 8. That's exactly corresponding to x being between 2.5 and 3.5. And you can do the algebra, right? If we look here, right, f of x minus 7 less than 1 absolute value, you drop the absolute values, it's between -1 and 1, you add 7 to each side, you get your function between 6 and 8. And that's exactly the same as if x is between 2.5 and 3.5. Now, the reason these are the same, well, I mean, there's a lot of reasons. We can see graphically, right? Literally, they're the same piece of the graph. But what we also could have done is we could have started with this and then worked our way towards this, meaning we could have said, well, okay, I'm going to start with the function minus 7 in absolute value being less than 1. And then I'm actually going to put what the function is in there. So I have the absolute value of 2x plus 1 minus 7 is less than 1. And the idea is I'm going to work on this until it looks like that, until I get to x minus 3. Usually, at least for linear functions, it's a very straightforward process. Okay, I'm going to factor out I'm going to subtract, and get the absolute value of 2x minus 6 less than 1. I'm going to factor out a 2. I'm actually going to bring out the 2. So the absolute value of 2 is just 2. I have 2 times the absolute value of x minus 3 is less than 1. And then I get to the absolute value of x minus 3 is less than 1/2. So a lot of times, with these kinds of ones where it's a linear function, it's very easy to get from a condition on where the function needs to live to a condition on where x needs to live. That's what I kind of think about. You're starting with, what do I need for the function to be true about the function? I want it to be close to its limit. What needs to be true about x? Oh, it needs to be relatively close to the value it's approaching. Okay. Now, what we're going to do is say, well, 1 is kind of far away from 7 still. Right? I would really like to actually be a lot closer to 7 than 1. So what if instead, here, in order, all the here, sorry. Suppose instead we are interested in the portion of the graph where our function's a lot closer to 7, where the absolute value of our function minus 7 is less than 1/10. So the question now is, can we find, I'm going to start using some of the language we're going to incorporate here. Can we find the number delta so that the absolute value of x minus 3 being less than delta describes the same portion of the graph? So here's the picture. There's our function, f of x equals 2x plus 1. I'm just going to eyeball it here. There's the value 3, there's 7. And what we're saying now, that's a 7, James? Okay. I keep grabbing this one pen and not throwing it away because it looks like there's still ink in it, but I have to throw away just pens because they don't work, even though I should. So now the idea is we're trying to go a lot closer. We're going up 1/10 and down 1/10. And we want to find what the bounds are, how close we have to be to 3. And we're not just going to say what it is. We're going to work with what we've got. So here's what we've got. We've got this. The absolute value of f of x minus 7 is less than 1/10. And we're going to do the same exact work. And this is really kind of often the process where you start with the thing you want and you work to get the thing you need. You're always starting with the difference between f of x and its limit less than some small number. And you're trying to figure out what is the difference between x and the value x is approaching need to be less than. So plug in our function. Our function is 2x plus 1. We got 2x plus 1 minus 7 is less than 1/10. Simplify. I got 2x minus 6 less than 1/10. So just because when you're factoring out a constant, if it's a positive constant, it just comes out as a positive. But if that was like a -2 and I factored it out, it would still come out as a positive because the absolute value of -2 is positive 2. So this is going to, I'm just going to pull that out as 2 times the absolute value of x minus 3 is less than 1/10. And then finally, dividing both sides by 2, the absolute value of x minus 3 is less than 1/20. That's our delta. Question?
Why do you leave it as x minus 3?
Because I want to know how close x has to be to 3. So here's what I would encourage you, really, really strongly encourage all of you to think about. When you see something like this, the absolute value of f of x minus 7, what I want you to think about is that means the distance between f of x and 7. This is the distance between two things. So I want that distance to be relatively small. I want f of x to be close to 7. The same thing is going on here. This is the distance between x and 3. And I want that to be relatively small also. Or actually, I'm going to back that up. I don't want it to be small. I need it to be small. Because I want this distance to be less than 1/10. I need this distance to be less than 1/20 for that to happen. So here's what we've got. We've got, again, here's where my penmanship is a barrier here. This delta here is 1/20. So we can go 1/20th to either side and have it work out. That we're still close enough so that our function is close enough to 7. So I'm gonna say it again. I'm gonna say it a lot of times. Yeah, question. That's a penman. That's a me writing the wrong thing. That's my brain saying 20 and my hand writing 12. Yeah. 120, not 112. Thank you. So once again, the idea is we're trying to find out how close do we need to make x to 3 so that our function is close to its limit. Okay. But we don't just want to keep picking numbers, right? I don't want to pick like 1/100th and then find the corresponding value, or 1/1000th to find, right? It's a tedious process. The idea is we're going to say, well, if we pick any small positive number, how close does x need to be to 3 so that my function is as close to 7 as that small positive number is? So here is the, that's all right. I do, it happens to me all the time. So here's the question that we actually want to answer. The question is, if we generalize and consider the absolute value of f of x minus 7 less than some epsilon, where epsilon is a positive number, can we always find a corresponding delta so that x minus 3 being less than that delta describes the same portion as the graph? As the absolute value of x minus f of x minus 7. That's an epsilon. Oops, that's a 3. Epsilon, not 3. And the answer is yes, we can. And the process is literally going to be, at least for this problem, it's literally going to be the same work we just did, except instead of saying there's a 1/10 there, we're going to write an epsilon. And we're going to do the same sort of algebra. So here's the graphical picture. So I'm going to draw like the same graph again. It's going to look virtually the same, except now the idea is there's our function, f of x equals 2x plus 1. And here's our point 3, 7. And the idea is now we're going, I'm going to make it a little bigger so I can actually draw it and have it not look terrible. Let's say that's 7 plus epsilon. And down here is 7 minus epsilon. And so we're going epsilon above, epsilon below. And we're going to find that we can get, welcome, come on in. Talking about some precise definition of the limit stuff. We can find a delta that gives us that. And the algebra is not terrible, at least if the function is linear. So if you're dealing with straight lines, this process is going to get boring. It's going to be the same thing over and over again. If you're dealing with other functions, it's a little more tricky, which we'll definitely get to. So what are we going to do? We're going to say, well, the absolute value of f of x minus 7 less than epsilon, replace your function with what it is. Do the same sort of work. So absolute value of 2x minus 6 less than epsilon, factor out the 2. Have 2 times the absolute value of x minus 3 less than epsilon. And finally, the absolute value of x minus 3 is less than epsilon over 2. So that is our choice for delta. So what we're saying here, one second, is that if delta is equal to epsilon over 2, then if x is within epsilon over 2 of 3, then your function will be within epsilon of 7. Question? Right. Sure.
But, you know,
Doesn't mean anything, but yeah. That is an excellent observation. That is very true. Sure. So that's a good question. So here's what I would say. Delta and epsilon are supposed to represent small positive. Epsilon is a small positive number. Epsilon could be 1/10. Epsilon could be 1 billion. And the point is that no matter how small epsilon is, let's say we picked epsilon equal to 1 billion. Well, delta would need to be half of that. Delta would need to be 1/2 billion. So if I want this function to be super duper close to 7, if I want it to be within 1/1 billionth of 7, x better be within 1/2 billionth of 3. So I can go up to 3 plus 1/2 billionth or 3 minus 1/2 billionth, and that's going to be close enough to 3 so that my function is close enough to 7. Because again, we're trying to quote unquote prove that the limit as x approaches 3 of this function is actually equal to 7. And again, limits are all about closeness. We're just trying to say that no matter how close you get to 7, no matter how close x gets to 3, the function gets close to 7. But you're right, there's no numbers eventually. We're just like, well, epsilon's a positive number. Usually we think of it as a small positive number. No. So in this example, well, I should say yes in this example. In this example, delta is always half of epsilon. Which makes sense if you have a function that has a line that has a slope of 2. Because any movement in the x value is going to get magnified by a factor of 2 when you find the y value. So x having a kind of an error, if you want to think of it that way, of epsilon over 2 means y will have an error of epsilon. But if our function had a slope of 3, then our delta would end up being epsilon over 3.
With x and, for example, in like epsilon always correlated with y.
That yes, I couldn't have said it better myself. Exactly. Delta is always how far x is from whatever x is approaching, and epsilon is always how far the function is from whatever it's limited. Yeah.
So I understand the like definitions and like the graphs and conceptual understanding behind like epsilon and delta for like two-sided versus one-sided. So what is like the mathematical process difference between the two of them if you were to like have a specific one from like for the right versus like for both?
So the right left thing, yeah, that's a good question. I don't actually have a great answer to off the top of my head. I guess if we were only approaching 3 from the right, then we would say that I'm not sure actually. I don't have a great answer for that.
It seems like they're virtually the same, except from like apart from like the actual limit notation, like plus.
Sure. No, you're right. As far as like actually so I would say we don't often do a lot of limit proofs of one-sided limits. But as far as evaluating limits, whether it's one-sided or two-sided, usually our process of doing like not this stuff, right? Not delta, but like the 0 over 0, factor cancel, whatever kind of stuff. That process is usually the same for one and two-sided limits. Typically, where two-sided limits usually come into play is when you're talking about piecewise functions. That's the most common example. Like, because if someone's trying to give you a function where a limit doesn't exist, the easiest example to come up with is a piecewise function, where you just have different pieces and different stuff's happening on either side. There are non-piecewise examples of limits that don't exist, but the easiest thing for a person to just make up on their own, like, oh yeah, piecewise function, totally good. Yeah. Okay, let's keep going with these delta epsilon proofs. So this leads to the idea of actually writing a proof. And so even though we have done the work, and your professor might have a different way that they like to write it versus how I like to write it. People have different ideas about how it's worked. There is kind of a formal way of writing up this proof. So here's the idea. We're going to prove the limit x approaches 3 of 2x plus 1 is equal to 7. And so I'm going to write out kind of what we're going to do, and then we're actually going to write the proof, and I'll be very clear. So to prove this, yeah, I want to say, yeah. We need to show that for every epsilon that is greater than 0, meaning epsilon could be really, really big, or actually epsilon could be super duper small. That's what we actually care about, but really epsilon could be anything from 1,000,000 to 1/1,000,000. So for every epsilon that's positive, there is a corresponding delta value. It is also positive. And here's where, so this next part's kind of like the meat of all of it, such that the following. Okay, I'm gonna say the words, then write the math. The words are the following. If x is close enough to its what it's approaching, then the function is close enough to this one. That's all we're saying. I want x to be close to, in this case, 3, and I want the function to be close to 7. Okay, here's the math. If 0 is less than the absolute value of x minus 3 is less than delta, then the absolute value of f of x minus 7 is less than epsilon. That's the whole thing. So again, let me read this to you in not math. What does that say? It says x is close to 3. That's all that says. It says it in kind of a fancy math way. And you could do more with it, right? If you really wanted to, you could say, oh, well, James, x minus 3 less than delta. If I really kind of work on that, that's the same as x minus 3 less than delta, bigger than negative delta. If I add 3 to everything, x is less than 3 plus delta and bigger than 3 minus delta. And one sec, it might be a little easier to see that way, that x is really, it is close to 3. It's it can only be delta more than 3 on the right and delta less than 3 on the left. Question. Sorry. Sure.
Like everything that we've always done is kind of been like a dependent and independent variable and
Sure.
the relationship between those.
So really, you should think of delta as a constant. I know we're giving it a variable name because it can be any constant. Right. And it should be a little specific, it's an arbitrary positive constant. Right. So we're saying that if x is less than whatever delta needs to be, then your function is going to be your function. If x minus 3 in absolute value is less than whatever delta needs to be, then your function minus 7 is less than whatever epsilon was decided to be. So to kind of complete this here, all this says is that f of x is close to 7. That's what those statements say. And so the idea is that for any epsilon could be super small. We can always find delta so that if you make x close enough to 3, how close? Delta close. If it's within delta on either side, then you will get the function to be as close as you want it to be to 7. How close? Within epsilon, either above or below. That's the whole idea. So here's the way we actually typically write up the proof. I have enough room? Yeah, I have enough room. So here's the proof. Let epsilon be greater than 0. We want, and I'm usually a little wordier than some people when I write it. So we want to find delta such that if the absolute value of x minus 3 is less than delta, then the absolute value of f of x minus 7 is less than epsilon. And then we say what delta is, because we've already done the work, right? We know from all the work we've done that in this example, delta needs to be half of epsilon. So pick or choose or whatever, delta equal to epsilon over 2. Then, and here's where people can be, some people like to show a lot of work here, some people like to show no work here. I like to show a little work. Then we get the following. That's not the way I would do it. then we say that James, come on. Sorry. Then the absolute value of x minus 3 less than epsilon over 2, because we're replacing delta with epsilon over 2. Right? We picked it, we chose, we did the work, leads to the following. That's going to give me that 2 times the absolute value of x minus 3 is less than epsilon. And if I bring the 2 in, it's going to give me the absolute value of 2x minus 6 less than epsilon. And then I can rewrite that as the absolute value of 2x plus 1 minus 7 less than epsilon. And that's what I wanted. Right, that's my function. So I just did the thing I said I wanted to do. Right? I said we want to find delta such that if the absolute value of x minus 3 is less than delta, then the absolute value of x minus 7 is less than epsilon. And then we said, oh, there's delta, it's epsilon over 2. So then we say the math we already did a bunch of times. That if this, then this, then this, then this. From the work we did before, right? From this previous page, where we said, right, oh, we want this to be true, and we worked it down to getting, oh, well, we need that. We want the absolute value of x to minus 7 to be less than epsilon. We need the absolute value of x minus 3 to be less than epsilon over 2. Typically, yeah, we definitely were here. F of x is just whatever we're taking the limit of.
We were given a function that was like x squared minus 9,
Mhm.
the one-sided limits, so we have to like put a hypothetical value for delta.
They're doing it that way.
Yeah.
Terrible.
And
The
so
worst.
that's why
Okay.
anytime I don't see
Yeah.
like fully tracked,
Right.
I start to think there's something hypothetical.
Yeah, so we'll talk, we'll get there today. But for now, for that, these ones, so I'll point out again, we're gonna do another example. The ones that are linear are pretty not terrible. The linear function, straight line, it's usually very not challenging to find what delta is.
So for this, everything that we need was given.
Right. Typically, well, no, you're right. I see what you're saying. Yeah. So let's look at another example. And we'll see it's going to be very similar to what we just did. Question. So right here. I should say there's usually one last step to writing this. Because I use then at the end, I usually like say therefore, or thus, doing fancy with my language there. Therefore, the limit as x approaches 3 of f of x is equal to, I forgot what it even was, is equal to 7. It is. So sometimes people do this work on the side and then they just jump from like here straight to the end and they don't show all these intermediate steps. It kind of depends what your professor wants you to do, is the unfortunate answer. All right, let's look at another example here. Let's find, I'm going to change one. So let's say we want to prove that the limit as x approaches 4, let's make it interesting, negative 5x plus 30. Well, we already know, well, we don't already know, but if we take a moment to do a calculation, we should know what this limit actually is. Okay, if I plug in 4, what do I get? Plus, so I get, right. So that's what the limit actually is. That's not the proof, right? That's just doing, like, if someone said, so I'll point out, if someone said, find this limit, great, you're done. We did the work. If someone said, prove this limit, that's when we have to use delta function. Or if someone said, show that this limit, show is a little, they should say prove if they want you to prove it. Oh, sorry, there is a question over here. If delta is already greater than 0, do we need to specify that the absolute value of x minus 3 is greater than 0? Yes, because the absolute value of x minus 3 is less than delta. So specifically, the reason you're specifying that, it's actually a good point. The reason we are specifying this is because we don't actually want x to ever equal 3. So we don't want to get 3 minus 3 equaling 0. So that's why we're saying that this difference has to be positive, not equal to 0. That's why we were saying that. Great, because again, I know I've said this a lot of times in previous classes, the limit really cares about what happens as x is getting really, really, really close to 3, but not equal to 3. We don't care what's actually happening at 3. We care what's happening as we get super duper close to 3. Or whatever you're approaching. Yeah. Mm-hmm.
For the problem we were just doing, what would they say if they wanted us to use it, but they were being like?
They would say prove. Prove. They should say prove this limit or use the proof. They might, the other words they might use is use the precise definition of a limit to show that this limit is limited. Yeah.
So I know in some of my.
Uh-huh. Right. Sure. Yes. In fact, so are you in Burke's class? Whose class are you in? Who? Okay. All right. Yeah, we can definitely, I think I have something like that over here. But so we'll definitely get around to that in a bit. So let's look at this one. So if I wanted to prove this limit, here's what I want. I want, say, well, the absolute value of the function minus its limit, I want that to be less than. That's the whole idea. And I'm going to eventually get to what I need. I'm going to need the absolute value of x minus 4 be less than whatever delta is going to be. Okay, it's the same sort of work, and it's not terrible. So did I leave myself enough room? Probably not. So we've got the absolute value of negative 5x plus 30 minus 10 plus an epsilon. Use an algebra. Take out the absolute value of negative 5x, 30 minus 10 is 20. That's an epsilon. I'm going to factor out a negative 5. Here's where I had you have to be a little extra careful. I'm going to factor out the negative 5 times the absolute value of x minus 4. Sorry, all that's still, excuse me, in absolute value. And then when the negative 5 comes out of the absolute value, it's going to become positive 5 because the absolute value of negative 5 is positive. This is going to become 5 times the absolute value of x minus 4 is less than epsilon. And then finally, we divide both sides by 5 to get epsilon over 5. That is our candidate for delta. That is our delta. Good? Yeah.
So with a linear function, there would be epsilon over like positive slope.
Right. I would say epsilon divided by the absolute value of the slope. Okay. Yeah. That'll always, that is a true observation that if you have a linear function and you're doing a delta epsilon proof, your delta will always be epsilon divided by the absolute value of the slope of that line.
So if there's no, if it's just x plus, excuse me, x minus 3, and delta is delta equals.
Right. If your function is a line with a slope of 1, like f of x equal to x minus 3 or x plus 7, then your delta will equal epsilon. Or negative x plus 7 also.
Function that's not a line, would it be that the slope at that one point?
Well, so I'm going to stop you because we're going to get there, and it doesn't really have to do with slope anymore. Yeah, it's a more complicated process when your function's not one. And unfortunately there's 2 different ways of doing it. There's kind of the way our textbook does it, which I kind of have come to prefer, and then there's the older way of doing it, which the textbook they used to use years ago did, and some people still teach it that way because that's the way they've always done it their whole life. I mean, I'm gonna say one slight correction. It's not x minus the limit, it's x minus what x is approaching. So I would say this is what x is approaching. And that's the limit of the function. And I'm not saying it's epsilon over 5 divided by delta. I'm saying that delta is equal to epsilon over 5. So in this example, delta ends up equaling epsilon divided by 5. Okay, so that's all the that's like the side work. We've done the side work. Now we're going to write the proof. Okay. And again, your mileage may vary, right? Some people like to be more wordy, some people like to be less wordy. So here's the way I typically write these proofs. Let epsilon be greater than 0. And my I will say, my thought process, my general kind of rules about proof writing, there's a lot about proof writing, which we're not going to get into the whole class, is that if you're writing a proof, here's what I like to do. You're going to tell them what you want to tell them. Then you're going to tell them. Then you're going to tell them what you told them. You really want to make sure it's clear that they know what's going on. So first, when I write this proof, I'm going to set it up and be like, here's what I'm going to tell you. Well, what do I want to do? I want to find a delta greater than 0 such that if the absolute value of x minus 4 is less than delta and positive, then the absolute value of my function minus its limit is less than epsilon. That's what I want to do. Now I'm going to tell you what it is. We found delta. It's epsilon over 5. So we're going to pick or choose, either word's fine there, pick delta equal to epsilon over 5. And then here's kind of the light version of the proof. Then, by the work above, if you like, it is, I think, not unclear that x minus 4 being less than epsilon over 5 eventually leads to the absolute value of f of x minus 10 being less than epsilon. In the previous problem, when we did this, I filled in all the steps, right? I wrote all my backwards work. Some people really want you to do that. Some people don't. It depends. I don't have a better answer other than that's some people want, some people don't. Okay. So then we tell them what we told them. So we did the thing we said we were going to do. What did we prove? We proved the limit. So I like to say, therefore, we have shown or we have proved that the limit as x approaches 4 of our function, you can either write f of x or negative 5x plus 10, is equal to, sorry, negative 5 plus 30, apologies, is equal to 10. And sometimes people like draw a little square here and they color it in, meaning we prove the thing we're going to prove. Yes. So I should say, yeah. And I did, but I didn't use those actual words. So I should say, right there, that is your if-then statement. If this, then this. That's what that right-hand arrow means. It's an if-then statement. Uh-huh.
Restating the parameters of the rules, and then from there restating our function, what we got, and then.
Right, to my mind, this is the answer. It's a lot, right? It's not just like a number or delta over epsilon or whatever. It's kind of the whole thing.
That's what we got, like our original function in relation to epsilon, right?
Yeah. Other comments, questions on it? I'm definitely coming back to your question in a minute here. So sometimes, so obviously, maybe not obviously, I think it would be difficult to ask you to do this question in a web work problem, right? Like, there's no way someone would be like, write this proof in a web work problem. You can't do it. So there are actually problems in web work that kind of get at the heart of this idea without actually having you write out this quote unquote proof. So let me look here real quick. I know I've got a couple examples. Yeah. Sure. This is where it gets, yeah. And so these ones, I think they all are kind of non-linear, which is fine. So before we get there, let's go ahead and kind of talk about how this is going to be hard. Because it is going to be harder. It's not always going to be a nice, easy linear function. If it is linear, though, we know what to do. And again, it takes a bit of practice. I definitely remember learning this when I took 21A, and it took practicing writing the proofs a number of times to really get an idea of like how they wanted it. And certainly my professor wanted it written differently than other people's professors, so I had to do it. This is how he wants it that way. So it takes some practice. You actually have to sit down and write them down a few times. And I think I've got a template. If it's not posted on Canvas, I will make sure to post it on Canvas about kind of how I like to do it. So can you explain in words how this proves the limit? Are we saying that an error margin X exists for which the error margin of Y is less than epsilon at 10? Those are not quite the words I would use, but that's essentially the idea. Yes. What I would say is we have shown, and again, I'm going to use the word attitude. So basically, here's what we've shown. We have shown that if the absolute value of X minus 4 is less than epsilon over 5, what does that really say? That says X is really close to 4. If X is within this small number of 4, then what do we get? Oh, we get that f of X is within this small number of 10. And again, that's the whole idea of the limit, that as X gets closer and closer and closer and closer to 4, my function is getting closer and closer and closer and closer to 10. Plus. So hopefully that helps with your question a little bit. Yeah, that does prove the limit equals 10. That definitely proves it. I know it feels kind of like, you're like, really? But like, yeah, because what we've said is the function gets as close to 10 as you want. How close to 10 do you want to be? 1 trillion. Great. Make epsilon 1 over 5 trillion. And your function will be within 1 trillionth of 10. That's pretty close to 10. But the point is you can get as close as you need to. Or as close as you want to, I should really say. By making X as close as you need to whatever it's approaching, in this case, 4. Okay. So now, here's where things are a little harder. We want to prove that the limit of X approaches 2 of X squared is equal to 4. And so here's the problem. Draw a picture here. So here's a decent approximation of my function. Let's say 2 is like right here. And so the problem is, if we make a fixed choice of epsilon, let's say up here, as you know, I've gone up epsilon, and down here, I've gone down epsilon. If we look at that, the corresponding deltas are not the same, right? This distance to the left here, this delta 1, is much bigger than this distance to the right here, which is delta 2. So for nonlinear functions, like X squared, a fixed choice of epsilon results in different deltas. On either side. In this case, on either side of X not equal to 2. So what do? Well, we still want this to be true, meaning we want the absolute value of f of X minus 4 to be less than epsilon. We still want to be in this range here. Literally, range, right? Y values. So which delta am I going to pick? Smaller one. Because if I pick the smaller one, so yeah, in fact, I'll draw this again. So what we're going to do is we're going to pick when this happens, we will choose the minimum delta value. So here's what I mean by that. Here's where I'm going to try and draw the same pictures again and make it not look terrible. Off to a good start already. Okay, so here's our 2. So if we pick the bigger value, it's going to be a problem. So here's delta 1. So if instead we pick both of them to be, so if we pick delta 1, then we're saying we're going to go this far to the left, and we're going to go the same distance to the right. And the problem is, if we go delta 1 to the right, we actually end up outside of the range that we want to be. You guys see that? Right, like we pick the bigger delta, you're going to end up with y values that are further away from your limit than epsilon with a y. On the other hand, if we pick the smaller delta value, so in this, which I'm calling delta 2, then we're only going to go that far to the left. And so we are definitely within the parameters that we need to be, right? We actually end up with a smaller range, but that's okay. It is okay to be stuck just in here. So that's the idea, is that when you have a nonlinear function like this, we're going to pick delta to be the smaller of the 2 delta values, or the minimum of the 2 delta values. Now, how does this work in practice? This is where things this is where methods differ. So I'm going to show you the method that is typically used in most classes now, but we will also talk about the other method in a moment here. So here's what we need. We need to describe the same region, the same portion of the graph using 2 different methods, meaning we need to talk about the same portion of the graph as the difference between f of x and its limit, and we want to describe it as the difference between x and when x is approaching, just like we did for the for the very first thing we did, right? We're really just trying to, right? We're trying to describe this portion of the graph in 2 different ways, as how it works for the y's and how it works for the x's. Okay, so I'm sorry, I need a picture. I'll draw this picture one more time, sure. Epsilon. I know it's not for the picture. Okay, so there it is one more time. And here's the idea. We need the following. We need both the absolute value of x minus 2 to be less than whatever our delta is. And we also need the absolute value of f of x minus the limit to be less than whatever epsilon is. Okay, so let's work with this first. That means we need x minus 2 to be. So this is where I'm going to use, I'm not going to say delta and negative delta because they're not the same. I'm going to say delta 1 on the right, delta 2 on the left. All right, I'm just looking at my picture. Or if you prefer, and this might be a little bit easier to see, let's see, yeah, sure. Yeah, okay, sure. I have x less than 2 plus delta 1. Now, here's where I have to be a little bit careful. I really should call this a negative delta 2 and say I have 2 minus delta 2 on the left. if the absolute value of x minus 2 is less than the number, that means it's less than some positive number and bigger than some negative number. It would be like if I had the absolute value of x minus 2 is less than 1/10, between 1/10 and negative 1/10. So same idea, a little hand wavy there. Okay, so this is what I need. I need x to be less than 2 plus delta 1 and bigger than 2 minus delta 2. Right, that's what those points are. Okay, so to get that, well, I need to think about what conditions I need to be true on epsilon. So I'm just going to do the same sort of work. So my function here is x squared, and the limit is 4. And I'm going to do the same kind of deal. You say, well, that just means that x squared minus 4 needs to be less than epsilon, bigger than negative epsilon. Or the function x squared needs to be less than epsilon plus 4, bigger than negative epsilon plus 4. Or you might prefer to write by this 4 minus epsilon. Right? So just graphically, here's what we've got. There's your 4 plus epsilon. There's your 4 minus epsilon. Okay, and so then what we're going to do is we're going to solve for x here. So we're going to have x is less than the square root of 4 plus epsilon and bigger than the square root of 4 minus epsilon. Oh, yep, of course, sorry. Let me zoom back out a tiny bit. Well, I'm actually what I'm really trying to get to how we find what is the minimum value for delta. So here's what we've got. We've got two inequalities for x. X has to be between these two things. X has to be between these two things. So we're just going to match them up. We're going to say this is that, and this is that. So what we've really got here is 2 minus delta 2. Sorry, you might want to see the things I'm writing. Equal to the square root of 4 minus epsilon. And 2 plus delta 1 equal to the square root of 4 plus epsilon. So now I'm going to solve for deltas. So solving for this delta 2 is going to equal, I'm going to add it over here, subtract it over there. It's going to be 2 minus the square root of 4 minus epsilon. Over here, delta 1 is the square root of 4 plus epsilon minus 2. And now the question is, which one is smaller? Well, if you've got the graph, oh, how do we know it's not minus the square root of 4 minus epsilon? So you're right, we did take the square root of both sides, but I will point out that, so right here, when we take the square root of both sides, both of these things are positive. And we know that x, right, x is getting really, really close to 2 here. So it wouldn't make sense to be x equal to the negative square root of 4 minus epsilon, because that would be really close to negative 2. So it's definitely a positive square root. Sometimes you do get a negative depending on where you are on the graph, but here we're definitely close to a positive number for x. So actually be between things that are close to 2, not negative 2. So which of these is smaller? Well, if I look at the graph, which one looks smaller, delta 1 or delta 2? Delta 1 looks like the smaller one, and it is the smaller one. And really what you can see in general is that if you have the graph, we won't always have the graph, but if you have the graph, the part that's steeper is going to correspond to the part that has a smaller delta. You've got more y change for the same, or I should say less x change for the same amount of y change. But we don't always have the graph, right? The graph isn't always going to be easy to draw, or we're not going to want to. So how do we figure out which of these is smaller if we don't have the graph? Well, pick a value of epsilon that's going to allow you to calculate something. I'm going to pick, what am I going to pick? I'm going to pick epsilon equal to 3. Why 3? Because it'll allow me to calculate one of these as the square root of a nice number. I can't pick 0. Epsilon has to be greater than 0. If I pick 0, you get both of these equal to 0, which is not helpful. So if we pick epsilon equal to 3, delta 2 would be equal to 2 minus the square root of 1. which is 1. And delta 1 would equal the square root of 7 minus 2. And the square root of 7 is less than 3. Because it's less than the square root of 9. So that is definitely less than 3 minus 2, which is 1. So this is the smaller one because it's smaller than 1. And that should work for any choice of epsilon you pick that's positive. So if you have something like this, and it's not easy to tell which one's the bigger one, which is the smaller one, you can literally pick a number for epsilon that's positive, plug it in, and see which of them is the smallest. Okay. So then, how do we write the proof? Right? This is all the background work to then write the proof for this thing. So here's how we write the proof. And this is where I do definitely get, I like to be concise. I don't want to write everything. I want to kind of write as little as possible. So for any epsilon greater than 0, if delta is equal to, let's see, we want to pick the smaller one, which we said was delta 1. So if delta is equal to the square root of 4 plus epsilon minus 2, then we can say that the absolute value of x minus 2 less than delta is going to lead to the absolute value of our function minus its limit, which is 4, being less than epsilon. Thus, the limit as x approaches 2 of our function is equal. We still did the same thing. We still showed that if x is really close to 2, then your function is going to get really close to 4. It just is less nice. But you could pick any value for epsilon you wanted. Something small, like 1/1000. And then if epsilon was 1/1000, it's not pretty, but delta would be the square root of 4 plus 1000 minus 2, which is a small number, right? Because you essentially have something that's close to the square root of 4, which is close to 2, minus 2. So a very small number. So we're saying that if your epsilon is small, pick delta equal to this, and then if x is that close to 2, then your function will be that close to epsilon. Question? Or, yeah. Sure. So I picked epsilon equal to 3. And I chose 3 because I saw that 4 minus 3 was a square number. The only I couldn't have picked any, right? 4 would have been too big to pick, right? So I picked 4, 4 minus 4 is 0. I mean, I guess you could have picked 4, but I wouldn't have picked 4. But I couldn't go any further than 4, right? Because 4 minus number bigger than 4 is going to be a problem. So I was looking for a number to pick for epsilon that would allow me to easily calculate one of these two values so I could see which of those two was the smaller one. Because it should be true that one of these, in this case, delta 1, is always smaller than the other one for any choice of epsilon that is possible.
In this case, when the deltas are different, you like make the one on the lesser delta, you always make that one negative.
I wouldn't say well, yeah, the one that's to the left. Yeah, we always want to make that one a negative one. So you're saying yes, yeah, exactly. So like right here is what she's saying. She's saying that right here, I called that negative delta over 2 because I know I was going that much to the left. Because if x was less than 2, right, a little left of 2, x minus 2 would be a negative number. We don't want it to be too negative. That's why we're putting a lower bound on there that's a negative. No, the same is not true. So for here's the nice thing about epsilon. Epsilon is the same either way. We're always going up epsilon or down epsilon. There isn't a different, there's not like an epsilon 1 and an epsilon 2. They're the same value. So we just say, yeah, I mean, you're right. The same in that you do get a negative, just like you normally would an absolute value kind of. So I suppose what we're really doing, if you want to be a little more specific about it, is we're saying we have the absolute value of x minus 2 is less than delta. Then we're saying x minus 2 is less than delta, bigger than negative delta. but then we're recognizing that those might actually be different values to the left and the right. So we're saying, oh, but that's really, delta 2 to the left, delta 1 to the right. That's what we're kind of doing there. Yeah. Definitely. So to prove the limit as x approaches a of f of x is equal to its limit, we show that for any epsilon greater than 0, there exists a corresponding delta. And the reason we say corresponding is because we always are finding delta in terms of epsilon. Delta corresponds to the value of epsilon in some way. A corresponding delta that's also positive, such that, here's where the meat is, if your absolute value of x minus what it's approaching is less than delta, then the absolute value of your function minus its limit is less than epsilon. That's the whole deal. Go ahead.
Is it incorrect to write the x approaching whatever next to the limit, or does it always have to be under? Is that like the function?
When you say next to, what do you mean by next to? I don't. Yeah, but so I guess you're asking, like, can we write it like, I mean like this, like. I don't want to say no, but I'm gonna say no. It's, you really should write it under, like 100%. Yeah. Yes. Sometimes you'll see, probably on web work, you'll see it like kind of to the right, but it's still lower, it's still a subscript, so it should be lower. Question?
Yeah, why are you able to plug in the deltas? Well, I guess that makes sense, but how can you tell that those are delta? Like when you're working out the epsilon thing?
So how can I tell that what is delta? Like in the previous problem?
Yeah, in the square root of negative epsilon plus 4.
Right.
How are you able to tell that that's delta 2, and how are you able to
Sure.
tell the other one is?
So the whole idea was that we said a couple times that we're trying to find the same portion of the graph. And in one sense, I described it as, well, my function needs to be within epsilon of 4. So I started with that. My function is within epsilon of 4. But in another sense, I'm describing it as x needs to be within delta of 2. Like that. So I'm describing the same portion. And what I'm trying to really do is I'm trying to figure out what x needs to be. I'm going to say the rest for everyone else here, just in case not everyone else is getting it. And so the idea is that you start with both these things, and we want both of them to be true, and then we work both of those inequalities down until we get to x in the middle by itself. So here x is between these two things, here x is between these two things. But to get the same portion, these things need to match. That needs to be that, that needs to be that. So that's how we actually start figuring out what delta 1 and delta 2 are, is by setting the 2 minus delta 2 equal to the square root of 4 minus epsilon, and 2 plus delta 1 equal to the square root of 4 plus epsilon. That's the way that the book likes to do it for this kind of delta epsilon. Question? Yep, I would say that that's the limit as x approaches a of f of x equal to L. And what I'm saying is we show that for any epsilon greater than 0, there exists a corresponding delta greater than 0 such that if, now I want you to read this as if the absolute value of x minus a is less than delta. What I want you to say in your head is x is close to a. That is what I really want you all to know when you read this, that x is close to a. How close? How close? Within delta. It is within delta on either side of a. Delta close. And when you read this over here, the opposite value of f of x minus L plus epsilon, I want you to read it that way, but I want you to hear in your head is f of x is close to its limit L. How close? With an epsilon. Again, we don't write those things down. When you're writing the proof, you're definitely not going to write that down, but that is what you should be thinking in the back of your head. Oh, yeah, this just means x is really, really close to a. Within delta to the right, delta to the left. This just means f of x is really, really close to its limit. With an epsilon above, with an epsilon below. Yeah. That is in general for any not linear function. So anything that's not a line, that's I would be a little stronger. You kind of have to do that. Now there is an alternate method which we'll talk about, but you can't just do the thing we did for lines, where you work with f of x and just solve it down to get something nice. So anything that's not linear, x squared, x cubed, 1 over x, square root, anything that isn't just mx plus b, you kind of have to do this. Yep, got to do this.
Is this like the alternative to what my professor was doing, which is like?
Yes, 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 yes. And we will get there, but most people have moved away from that because it's not as nice, honestly. But that doesn't mean it doesn't work. You should probably, so we will talk about the other way in just a second. Let's see, there's someone else here. Let's see, what have you got here? How do I know when there are two differing deltas in the graph and when they equal one another? Is it only equal when it's only equal when the graph is linear. Yep. So that nice, the way we did it for the first two examples where it was nice and linear, you just got like, delta equal to epsilon over 5 or delta equal to epsilon over 2. It's only going to work if it's linear. It's not going to work for any other non-linear function. So let's look at a couple things over here. So for example, so we'll do another example like this in a minute, but let's go ahead and address a couple similar-ish questions to get at the same point. So here is a question from someone's homework assignment, Professor Burke's homework assignment. So here's a question that's getting at this proof idea without actually making you write a proof. So the idea is, black pens just don't seem to want to work as well. I don't know why. It's terrible. I want to write in black, but I guess I'm going to write in blue. So find a value, delta, positive, such that for 0 less than the absolute value of x minus here 20 in delta, we have that implies that the absolute value of my function, which is 100 over x minus my limit, which is 5, is less than epsilon. And we're going to set a value for epsilon of 0.9. So this is a common web work question to kind of get at how do you do this delta epsilon sort of proof. So I want to point out, I think, well, in fact, let's actually do it. So just to kind of be super clear, the limit we're trying to show exists, or the limit we're trying to do the process for the proof for would be the limit as x approaches. Well, what is x approaching? What is x really close to here? X is close to 20. What's my, well, let's actually, I'm just going to write the function. Let's actually plug that in. What is the function that we're dealing with? What's the only thing that seems like a reasonable candidate for the function? 100 over x. And that's kind of the only functional thing we have. And then, well, we don't even have to look at this. If you plug that in, what would that value end up being? Right, which again makes sense because we should have, right, that this is just your f of x minus the limit as less than an epsilon. And this is your x minus what it's approaching less than delta. So they've given us all the pieces of information except for what delta is. and they're asking us to find the delta. So here's the graphical interpretation. 100 over x, okay, sure. So there's the right side of 100 over x, and we're looking at when we're getting close to 5. And what we're asking is, okay, sorry, not when we're getting close to 5, we're actually getting close to 20. X is getting close to 20. The function should be getting close to 5. And so what we're asking is, how close to 5 do we want to be? Epsilon in general, in this specific problem, what's our epsilon? Right, so we want to be either at 0.9 above or 0.9 below. And we're going to try and find it's over there, the corresponding delta. So there's your, I should have really done delta 1 on the left before because that's more typical. So here's my delta 1, and here's my delta 2. And just from the picture I've drawn, which one seems like it's going to be the answer? Delta 1. Now, maybe I drew it poorly, right? Maybe this is a terrible graph, but I didn't, right? This graph is definitely steeper on the left and not as steep on the right. So we're pretty sure it's going to be delta 1. I'm still going to do the same sort of work I would have done before, though. So I'm going to start off with both inequalities. I'm going to start off with the absolute value of x minus 20 less than delta, which is going to just really quickly lead me to x minus 20 between delta 2 on the right, negative delta 1 on the left. Right, because this is 20 minus delta 1. And this is 20 plus delta 2. And then I mean, really, you could even just look at the graph to get there and be like, oh, I'm adding 20. So I'm going to get 20 minus delta 1 is less than x is less than 20 plus delta 2. All right, I did. You're right. It's the last time I switched them. It doesn't really matter what you call them as long as you're consistent. So you can call this one whatever you want. You can call this one whatever you want. Just make sure that you're doing your value minus the one to the left, your value plus the one. And then we also have the inequality here. We have 100 over x minus 5 is less than 0.9. So we're going to work on that, and I probably need more room. It's all right. So I have 100 over x minus 5 is less than 0.9, bigger than negative 0.9. And then add 5 to everything. So 100 over x is less than 5.9 is bigger than 4.1. And then we're going to take, well, so there's a couple ways you could do this. You could multiply everything by x. That's not what I really recommend. I would take the reciprocal of all parts of this inequality. But I'll remind you, when you take the reciprocal of an inequality, you change the direction of the inequality. Because here's what I always go back to. If 2 is less than 3, which it is, and I take the reciprocal of both sides, what's bigger, 1/2 or 1/3? 1/2 is bigger than 1/3. Oh yeah, we changed the direction.
One with x and delta and the other with like our function f.
Right. And the idea is to get both of them to a place where x is isolated in the middle. So I'm going to take the reciprocal of both sides here. It's going to get kind of ugly. I'm going to have 1 over 4.1 is less than x over 100. Oh, sorry, is bigger than x over 100 is bigger than 1 over 5.9. And then finally, I'm going to multiply everything by 100. So 100 over 4.1 is bigger than x is bigger than 100 over 5.9. Okay, so let me ask you all. So does 100 over 4.1 match up with the 20 minus delta 1 or the 20 plus delta 2? Sure. So does this thing here, which of these two should that match up with? The 20 minus delta 1 or the 20 plus delta 2? Right, because it's the thing that x is less than. So maybe I should rewrite this inequality so that it looks like it's in the same order. I also have x less than 100 over 4.1 and bigger than 100 over 5.9. And now I'm just going to set these equal to each other. So I'm going to set 20 minus delta 1 equal to 100 over 5.9 and get delta equal to delta 1 equal to 20 minus 100 over 5.9. Which should be the smaller one, but we'll check to see. And then we're also going to get delta 20 plus delta 2 equal to 100 over 4.1. So delta 2 is equal to 100 over 4.1 minus 20. Now let me ask you all. 100 over 5.9, 100 over 4.1 are both going to be kind of close to 20-ish. Which one's going to be closer to 20? Actually, I don't have a good, I mean, I thought it's not super easy to tell which one's going to be closer to 20. So that's when I would use a calculator. I didn't bring my good calculator, so I have to use my fun phone calculator. Okay. So using the lovely phone calculator that I do not recommend. So let's see, I have 100 over 4.1 minus 20. Oops. So I'm going to get 4.39 approximately. And 100 over 5.9. And if I subtract 20 from that, 20 minus 16.949 is approximately 3.06. 0.05. So delta 1 is the smaller value. Right? We see that with our eyes. It is right there for sure. Delta 1 is the smaller of the two. It's about 3.05. Now, I will say that doesn't feel like a very small delta value, right? It seems kind of big, right? We were talking like delta being like 1 billion, but that's because our epsilon was relatively big, especially for a function that has a lot more play in the x direction, right? You have to really, right? If your function is 100 over x, you really have to increase x by a lot to get the function to change its output value by a small amount. And I thought I saw a hand somewhere. Good, you got it. If you don't know which one is going to be smaller, yes. But if you draw the picture, and you're like, well, clearly the left one's smaller, you only have to calculate. Right. So what I really know, what the guiding kind of light here is I'm trying to get both of these inequalities to a place where x is by itself in the middle as just 1 times x, not divided by, right, not 1 over x. So I'm really looking, I had to do the reciprocal to get x out of the denominator. Question over there. Oh no, as behind you. I think I'm getting 3.05. Let me double check. Maybe yeah, it is, right? Is it 5.9? Is it 4. Did I make a mistake? No, okay. So let me check one more time. So 100 divided by 5.9, I'm getting 16.94. And then if I do 20 minus that, which is annoying in this calculation, I'm just going to subtract 20 and then say it's the opposite. If I subtract 20, I get negative 3. So yeah, it should be 3.05. That could be it. My 9 sometimes look like 4s. So that's how you would tackle a problem like that in web work, right? It's still the same idea. Now, the difference between this and web work is if I was trying to do this as a proof, I would have not used a real number here. I would have used epsilon. So let's actually talk about how we would write the proof for this one. So yeah. Because the question I was asking was which of these 2 inequalities this should correspond to. So I was asking, does it go here or does it go over there? But it definitely goes here because it's the one that x is less than. Let's see. Sorry. How do we know when there are 2 different deltas in the graph? Oh yeah, we got it. Does this lesson correspond to any chapter in our textbook? Yeah, I think it's like chapter. I know it's a certain chapter in the textbook. I think it's 2.3, 2.3-ish, maybe. It should be the one that's called like the precise definition of the limit. Okay. I mean, I always have another problem lined up, but actually, before I do want to actually talk about how you would prove this one actually, instead of just solving this one value. So we're gonna do the same sort of work. It's not gonna be too terrible. So here's what we want to do. We want to now prove that the limit as x approaches, what was it, 20 of 100 over x is equal to 5. And so I'm not going to draw the picture this time. I'm just going to try and do the work. I'll try and do it in the most efficient way I can, which is probably not very efficient. So we know we need two things. We need the absolute value of x minus 20 to be less than delta, and we need the absolute value of 100 over x minus 5 to be less than epsilon. Those are the things we need. All right, so this one, x minus 20. So this is where you do, so I would say, I'm not going to write the picture. You're going to have to know, if you're not going to draw the picture, if it's nonlinear, your delta 1 and your delta, right, you should have different deltas on either side. So we're going to say that x minus 20 is less than delta 2, bigger than negative delta 1. And then x is less than 20 plus delta 2, bigger than 20 minus delta 1. Okay, I'm stopping there. I've got x in the middle. Great. Now I'm going to do it over here. So 100 over x minus 5 is less than epsilon, is bigger than negative epsilon. We don't need different values for epsilon. The same on the other side. So then I'm going to try and isolate x. I'm going to add 5 to everything. So 100 over x is less than 5 plus epsilon is bigger than 5 minus epsilon. Take the reciprocal of both sides, remembering that I have to change the direction. So x over 100 is bigger than 1 over 5 plus epsilon and smaller than 1 over 5 minus epsilon. If you don't love writing in that direction, change it. Right? We can totally write this thing on the right, this thing on the left. So I'm going to say, I'm going to multiply everything by 100. So it's going to be 100 over 5 minus epsilon. And let's write it over here. So x is less than 100 over 5 minus epsilon and bigger than 100 over 5 plus epsilon. Which makes sense because x should definitely be bigger than the smaller thing, and the smaller thing has a larger denominator, right? The bigger the denominator, the smaller the fraction. Okay, so now we are at the place where we're going to set things equal to each other. Now we know the answer should be that delta 1 is the smaller one, because we already did the work with the previous example. But let's actually do it. So if I have, I'm going to do it this way, 100 over 5 plus epsilon equal to 20 minus delta 1. And delta 1 is going to equal 20 over 100 over, come on, James. What's it really going to be? 20 minus 100 over 5 plus epsilon. And similarly, if I look at this equality, 20 plus epsilon, delta 2 equal to 100 over 5 minus epsilon is going to lead me to delta 2 equal to 100 over 5 minus epsilon minus 20. We know delta 1 is smaller, but we might not know it in our hearts. So pick a value for epsilon. It's going to make it easy to calculate at least one of these things. Recognizing that 5 is out of bounds. If you go bigger than 5, you're going to be in trouble. So I might pick 4. I might pick 1. I don't know. 4 seems reasonable. So if I pick epsilon equal to 4, then delta 1 equals 20 minus 100 over 9. I'm not thrilled about that, but fine. And delta 2 is 100 over 1 minus 20, which is 80. I'm pretty sure delta 1 is smaller because 20 minus a positive number is smaller than 80. Right? Like, no question. I don't need to do any more work. I could. 100 over 9 is like 11-ish. So 20 minus 11-ish is 9-ish. But delta 1 is our smaller. Okay, so then we actually have to write the proof. And again, we're going to be very succinct. So here's the proof. for any epsilon greater than 0. Let me make sure I write this down the way I want to write it down. Always good to look at the previous one. Yeah. If delta equals, there's my delta, 20 minus 100 over 5 plus epsilon, then we can say that what we want, the absolute value of x minus 20 less than delta, implies the absolute value of my function 100 over x minus 5 is less than epsilon. Thus, the limit is proved. The limit as x approaches 20 of 100 over x is equal to. So I know it's kind of a lot. It's the same process every time. Well, if it's linear, it's the easy process every time. If it's non-linear, it's this harder process every time. So someone asks, is there an algebraic way of showing that delta 1 is smaller than delta 2 without like picking a number to plug in? Probably. It's probably more work though. So you could probably like maybe set these equal to each other in some way and figure out which one's going to be bigger. But I really think the easier way is either to look at it graphically or to just pick a number for epsilon. That's probably the preferred way. I don't think there's not a good way of just doing that. Ida, you said you had a question or something next.
That's like requires us to do like more like factoring and like involved steps for this.
So I think what you're talking about is the other way of doing it, because doing it this way never requires factoring. I've got an example if you want. Let's see here. And I apologize in advance because it's been a while. I don't do it this way anymore. So I'm not as good at it, but that doesn't mean I can't do it. So go ahead. Yeah. So here is the alternate way of doing this. So let's prove that the limit as x approaches 3, x squared plus 1 is equal to 10. And we're going to do this a different way. So this is actually more similar to kind of the first way we did with the linear examples, where we're going to try and look for a condition on x minus 3. So we need the absolute value of x minus 3 less than delta, and the absolute value of the function minus limit to be less than epsilon. So here's what we're going to do. Well, yeah, it's kind of, yeah, okay. We're just going to do it. So I'm just going to work on this. So I've got x squared plus 1 minus 10 less than epsilon. And then I've got the absolute value of x squared minus 9 less than epsilon. And now here's where things get a little weird. I'm going to factor this at the absolute value of x minus 3 times x plus 3. Now here's where we're going to run into an issue. I know the opposite of x minus 3 is going to be less than whatever I pick delta to be. All right, so I'm then picking delta less than some epsilon over something. But the problem is x plus 3 could still be whatever. So what I need to do is I need to kind of set an upper limit for how big delta can be. So when you've got extra factors left over that are not just the thing we want. And again, so if your teacher is not doing it this way, you don't have to do it this way. You probably shouldn't do it this way.
To be clear, if we're not doing it this way, then we just take x squared minus 9 and just
proceed as we go. In fact, we'll probably go ahead and do it that way at the end, or at least, yeah. It's not crazy. It's definitely the way I learned it when I was student. I agree, but I will tell you, it didn't always feel nicer to me. Like doing it the other way I've just showed you guys 2 or 3 times really felt like weird. Like this seems so weird. This other way was so nice. So it's really just whatever your normal is, right? Right. But your professor might expect one way over there. You should. Right. Right, exactly, I'm not. So let me go ahead, so here's what we're gonna say. We're going to assume. We're gonna make an assumption. We're going to assume the delta is less than, pick a nice number. Now, there's a couple things to be clear about delta. If you have a function that might be undefined somewhere, you definitely want to pick delta so that you don't go past that point. Like in the previous problem, in this problem here, if I had say, so like when I was looking at this 100 over x minus 5, if I had picked, you know, my delta to be a number where I'm getting too close to x being 0, that's a problem. So I want to avoid, right? So like here I've got x minus 20 less than delta. I want to make sure that delta is less than 20, because right, 20 would be too big, or 20x would be right on the border, because if delta is as big as 20, the next could be as small as 0, and 0 is a problem for this one. So make sure you're not getting to a place where a function might be undefined. Usually it's not a problem. If it is, just pick a smaller delta. So we're going to assume delta is less than 1. It's a pretty standard choice if there's no other thing preventing you from doing it. So here's what that means. Well, we're going to make the assumption that x minus 3 is less than the absolute value of x minus 3 is less than delta. So if I make this assumption, I'm saying that the absolute value of x minus 3 is less than 1. And then I can say, well, that means x minus 3 is less than 1, bigger than -1. And then what I really care about is what x plus 3 is going to be less than, because that's the problem piece that's left over here. So I'm going to add 6 to everything. Well, because the thing I want is the thing I know something about. I know I'm going to say at some point the absolute value of x minus 3 is less than delta. And so if I'm saying delta is less than 1, then I know, because I've said that the delta is less than 1, that the absolute value of 3, the absolute value of x minus 3 has to be less than that 1. And then I can get a condition on the other factor that's a problem. So if I add 6 to everything, 6 plus -1 is 5. X minus 3 plus 6 is x plus 3, and x 6 plus 1 is 7. So what I can say for sure is this x plus 3 is less than 7. So I can say, oh, here's what I really have. I have the absolute value of x minus 3 times the absolute value of x plus 3 is less than the absolute value of x minus 3 times 7.
So we're adding 6 to get to a point where we have something that looks like our problem.
Yes, right.
Can you explain that last bit you wrote? Because that's what like had me lost when you were explaining.
Right. So the thing is, we're trying to say something about this. Right. And I know, so because I said that x plus 3 is less than 7, it is true that the absolute value of x plus 3 is less than 7. And then I'm going to say that this is less than epsilon.
Is it possible to use like, I don't know, like different colors or circles or something? To like circle each respective part and like show where they come from? Because like looking at this, I'm having a hard time conceptualizing like, are you just like creating like equivalencies between the inequalities and creating one larger one, or?
So what I'm doing is I'm trying to get to a place where I can say that the absolute value of my function is less, is right, it's equal to this, equal to this, equal to this, it's less than that. And then I want that to be less than epsilon. I'm kind of putting an intermediate inequality in here to get to what I want, which is a little tricky. But basically what I'm doing from say this step to this step is I'm using the fact that the absolute value of x plus 3 is less than 7. From all this over here. Because that's because, well, I should say sometimes it is. Because for just as a kind of counterpoint is if we ended up having something where like it said there was a 1 over x plus 3, then we would end up doing this. 1 over x plus 3 is smaller than 1 over 5, is bigger than 1 over 7. So we really care about the part that x plus 3 is less than. So that's the direction of the inequality we care about, which is why this is the number important. So we're almost there. Then we can say, okay, so that means the absolute value of x minus 3 has to be less than epsilon divided by 7. So what's our delta? Oh, question.
Multiply 7. Why not? Why not? Why-
So what we're because what we're saying is, so we're saying, what I would say is we're not multiplying 7, we're multiplying by x minus 3 absolute value. So I took that inequality, the absolute value of x plus 3 is less than 7, and then I multiply both sides of that by the absolute value of x minus 3. Right. No, don't be sorry.
Why mathematically falls between epsilon and our original kind of like.
Sure. So what I should say is this. I should say, this is what we want. We want this. We want the opposite value of x squared minus plus 1 minus 10 to be less than epsilon. So what we're going to do is we're going to do whatever we need to get there. Meaning, at this point, I'm saying, well, I really want this to be less than that, but I don't know how to make that true. So what I'm going to do instead is say, well, there's something I know that this is less than. I know that this for sure is less than that. Right? Because we said, right, assuming this, assuming the delta is less than 1, I can say for sure that the opposite value of x plus 3 is less than 7.
I understand what you're saying, but the point is that in the whole assumption that we made, we were only calculating x minus 3 when we were doing the math, so how are both of them included for it to fall between them?
Well, so let me ask you this. Do you agree with that? That the opposite value of x plus 3 is less than 7. Cool. So for any inequality, I can multiply both sides by whatever positive number I want, and it won't change things, as long as it's the same number on either side. So all I'm doing at the next stage is I'm multiplying both sides by the same positive thing. So that inequality is still true. And the reason I'm doing it is because I want this thing here to be less than epsilon eventually. And so I'm using this intermediate thing, which I'm saying, well, I'm just going to say that that's less than epsilon. And then the thing I want to deal with is less than that, and it works out for me.
So in that case, what you just did, kind of just canceled out the x plus 3.
Yeah,
Oh,
you could say it that way. So then here's kind of the sum up. We're going to prove this. Our proof is going to rely on choosing delta equal to the minimum of 1 and epsilon over 7, which I find annoying, but it is the way it works.
Because we made the assumption about delta, we have to.
Right, because what if epsilon was 10? Well, then we've made assumptions that still mean this has to be less than 7 here. So we have to be like, well, if epsilon's 10, we're going to take delta equal to 1. Because that's still going to be fine. Right? If epsilon's so big, we can pick delta to be this 1, and it'll definitely get us what we need. So then if we were going to write this proof here, the proof would be let epsilon be greater than 0. We want to find delta greater than 0 such that if 0 is less than the absolute value of x minus 3 is less than delta. And I should maybe write it top here, right? We are proving the limit as x approaches 3 of x squared plus 1 is equal to 10. So we want to find our delta such that if this is true, then the absolute value of our function minus its limit is less than epsilon. So then we're gonna say what delta is, and we found it already, we did the work, so we're gonna say, okay, pick delta equal to the minimum of 1 comma epsilon over 7. And then this is where I would be succinct is the word I'm gonna use. I would not write all the things. I would say, then we have shown, maybe I might refer to the work we showed on another piece of paper, maybe. We have shown that if the absolute value of x minus 3 is less than our delta, still bigger than 0, then we get the absolute value of x squared plus 1 minus 10. It feels kind of dumb in some ways. Like you're like, well, I wrote a thing and I'm kind of writing the same thing again. That is what the process is, unfortunately. So thus, we can say the limit as x approaches 3 of x squared plus 1 is equal to 10. Yeah.
So, this is actually just the same problem, just like minus the forget.
Sure. Yeah. Mm-hmm.
That weird inequality he did, he labeled that 1. And then for the final answer, he said, well, if x minus 3 is less than delta, then he did the inequality with the epsilon answer. And then that is equivalent to the weird inequality, then by number 1,
Sure.
x squared minus 9 is less than epsilon. Is that?
That's kind of what I'm saying there. I'm saying then by the work we did and all this other stuff over here. Yeah. Let's see. Having a hard time with that last step. How do we go from the 3-part absolute value inequality to the 2-part one? I'm guessing you're asking about this part right here. So the way we went from, so basically all I did to go from here to here was just focus on the second part there and divide both sides by 7. Because what I'm really trying to get to is some condition on the absolute value of x minus 2. And I'm saying, oh, that's my delta. Yeah.
Why for the proof that we just did,
Mm-hmm.
why did we choose, pick a minimum?
So because if you're doing it this way, you have to do the same because we said to do this problem, we're going to assume that delta is smaller than 1. We made that assumption. And then after we made that assumption, we were able to say, well, as long as delta is less than 1, then we can pick delta equal to epsilon over 7. However, if delta was larger than 1, I always do this thing here. Sorry. Stop. Or if epsilon was a value that made epsilon over 7 larger than 1, we wouldn't want to pick that. So if epsilon was 14, you wouldn't say delta is 2. Say we have to pick delta equal to 1 because we have already said that delta has to be, or something less than 1, I suppose. We pick something less than 1. So that's why we're saying here that we're going to choose delta to be the minimum of 1 epsilon over 7. Because if epsilon over 7 is bigger than 1, we're going to pick it to be 1. If epsilon over 7 is smaller than 1, then we're going to pick it to be epsilon over 7. So that no matter what happens, either way it works out. I would say times the 7 in your middle inequality there. Should be the absolute value of x minus 3 times 7. Not actually. I'll address that in a minute. So, okay, it's a lot, and I would say it requires practice. You have to practice this if you want to understand it. There's no other way to learn it other than just by repeating it a number of times to really kind of see what's going on. So let's look at one last example. So let's say we want to prove, well, at least you can't always choose 1 as your maximum possible value. It's a good starting place, but let me say actually this next example is a good example of that. So let's say we want to prove the limit x approaches 1 of x minus 7 over x plus 1 is equal to, if I plug it in, I get -6/2, which is -3. Okay, so. And yeah, we'll do it both ways. So here's the alternative way that I wouldn't do unless you have to. That's what I would say about the alternative. So here's the alternative method. We're going to find delta greater than 0 so that if absolute value of x minus 1, x we're approaching 1, is less than delta, then the absolute value of my function minus my limit is less than epsilon. I'm going to work on this. I'm just plugging things in. And I'm probably going to get a common denominator here. So I've got the absolute value of x minus 7 minus 3 times x plus 1 all over x plus 1. And simplifying the top here, I've got, let's see, x minus 3x minus 7 minus 3. Right, minus 7 minus 3. I feel like I'm making a mistake there. Minus 7. Yeah, I feel like yeah, I did make a mistake, right? Right, it's not or I should point out it should be f of x minus the limit, right? And the limit is -3. Right, it's f of x minus the limit, which is -3. So that should be x minus 7 over x plus 1 minus -3. So that should be a +3, which means instead of having x minus 2x, I should have x plus 3x, which is a positive 4x. And then minus 7 plus 3 is a minus 4 all over x plus 1. Factoring out of 4, I've got 4 times the absolute value of x minus 1 over x plus 1. Which, if we want to break it up, is going to look like 4 times the absolute value of x minus 1 over the absolute value of x plus 1. Okay. The problem is the x plus 1. Right? We know that x minus 1 is going to be less than delta. Right there, right? We know this. What we need is to say, well, let's pick a delta or an upper bound for delta so that we can then get a condition on the absolute value of x plus 1. So here's what we're going to say. We're going to say that assume delta is, I'm going to pick 1 again. It doesn't end up being an issue. You can't always pick 1 here. Yeah, 1 is it fine? Yeah, it's fine. Let me show you. So if we start with x minus 1 and absolute value less than 1, right? Because that's what we're saying. X minus 1 is less than delta. Just plopping in delta right there. So then we have x minus 1 between 1 and -1. Adding 1, we have x between 2 and 0. Let me ask you, what value of x would have been a problem to plug into this expression? -1. So if we had picked instead delta to be, say, less than 2, then we would have had x minus 1 between 2 and -2. And if we'd add 1 to everything, we would have had x minus 1 between 3 and -1, which would have been a problem because -1 is problematic. So that's the thought process. I'm trying to avoid picking something where x is eventually going to lead to problems over here. But actually what I really want is that. So I should add 1 to every side and say x plus 1 is between 3 and 1. And then since this is in the denominator, I'm going to take the reciprocal of all sides, right? So here's what you can see, right? If that was a 0 there instead of a 1, taking the reciprocal would be a real problem. So 1 over x plus 1 is less than 1. This is where we care about the other side of the inequality instead, because of the fact that we're flipping things. So now here's what we're going to say. We're going to say that this thing, 4 over, I'm going to rewrite this as 4 over the absolute value of x plus 1 times the absolute value of x minus 1. And I'm going to say that that's less than 4, well, 1 over x plus 1 is less than 1. So 4 over x plus 1 is less than 4 times 1. Times the absolute value of x minus 1. If that is true, if 1 over x plus 1 is less than 1, then 4 over x plus 1 is less than 4. And then you can say, well, that's what we want to be less than epsilon. Let's think of those pens away. Just don't want to throw pens away. It seems wasteful. So then the absolute value of x minus 1 is going to be less than epsilon over 4. From that. So let me spell it out a little bit more. I guess I should have written it like this. So we have this. We have 4 times the absolute value of x minus 1 over x plus 1. I'm going to break it up into all 3 parts. So it's 4 times 1 over the absolute value of x minus 1. Sorry, plus 1. Absolute value of x minus 1. By the way, it is 11:51. If you need to go, you're certainly welcome to go. I'm just going to wrap up here. And then what I'm saying is this part here specifically, this part here is less than 1. It's also bigger than 1/3. I don't care about it. It's less than 1. So then this is less than 4 times 1 times the absolute value of x minus 1. And then I'm going to say that I want that to be less than delta. Sorry, epsilon. Because what I want is, right, this here still, as a reminder, this here is still my absolute value of f of x minus my limit. And I want that to be less than epsilon. So here's a thing that is less than, or equal to actually. And here's the thing that that's less than. And then I'm going to say that that thing is less than that. So that I get the inequality. So now we have the absolute value of x minus 1 is less than epsilon over 4. And that is my choice for delta. Right, because this inequality, 4 times a thing is less than 4 times 1 times the thing. I'm just saying that this is less than 1. Multiply by 4, multiply by other positive thing, the inequality is still retained. Then I put a 2 there. Yeah. So then we could write the proof. We would say, so I don't really want to write all the time, but we would do the same sort of proof we did before. We did the whole sum up. We were going to pick delta. So we're going to pick delta to be the minimum of 1 and epsilon over 4. Right, exactly. Correct. Sure. So the way we would do it the other way is we would say, so I would start with, so we have these 2 things we want x minus 1 to be less than delta in absolute value, and we want the absolute value of x minus 7, x plus 1 minus 3 to be less than epsilon. So we work on this. X minus 1 is between delta 2, delta 1. We add 1 to both sides. Again, if you need to go, totally fine. I know I'm way over here. And then we do the same sort of work over here. So we'd have x minus 7 over x plus 1 plus 3 between epsilon and negative epsilon. And then it gets a little messy. We add 3 to everything. 3 minus epsilon is less than x. Thank you, yeah. Sorry, getting a little too fast here. And then, yeah. I'm trying to remember how we would do this. Oops. Yeah, let me multiply. So it does get messy. We multiply everything by x plus 1. And then we have to distribute. Yeah, it gets real gross here. So we have negative 3x minus x epsilon minus 3 minus epsilon less than x minus 7 less than negative 3x. Sorry, plus x epsilon minus 3 plus epsilon. And then we collect, so then I would add 3x to everything and add 7 to everything. So if I add 3, yeah, it's real good. So if I add 3x, I'm going to get and add 7 to everything. So I'm trying, because I'm trying to get the x in the middle. What I'm trying to do is I'm trying to get to a place where I have x isolated in the middle. And I think I need a little more time to work this one out because the algebra is just a little complicated.
Yeah, but basically, the idea is you just keep going then.
Eventually, we'll get to a place where we have x between two things. And then we'll say that that thing there is that thing there, and that thing there is that thing there.